Next is the new section, section 72. Here we are going to look at the uniqueness of Taylor series and No랑 series representations, which means there is a unique representation for Taylor series and No랑 series. Theorem 1. If a series given by this, summation n is equal to 0 to infinity an times g negative g naught to the n, converges to f of g at all points interior to some circle given by absolute value of g negative g naught is equal to large R, then it is the Taylor series expansion for the function f in powers of g negative g naught. We prove this theorem by considering two different Taylor series representations, possible case, but individually, but eventually we get a single expression at last. Okay, the first expression is given by this, exactly given in the theorem here. For another expression, representation, we use index of summation m here. Difference is on the use of summation index here. Then by applying to theorem 1 in section 71, we may write integral along to control c, g of g times f of g dg is equal to summation m is equal to 0 to infinite am times integral control c, g of g times g negative g0 to the m dg, where g of g is any one of the functions defined by this. G of g is equal to 1 over 2 pi I times 1 over g negative g naught to the n plus 1. Here n goes from 0 to 0, 1 to the infinity here. And c is some circle centered at g naught and with radius less than large r. Okay? Okay, in view of extension 3, in section 55 of Cauchy integral formula, we find that this equality holds because g of g is given by this. So just simply replace by this definition, this formula, g of for g of g here, then we get this. And extension 3 in section 55, we use that. If we use that, we get this result. The nth derivative of f of g naught divided by n factorial. And since integral along to control c, g of g times g negative g naught to the m dg, here, g of g is given by this, is replaced by this for the g of g here, then we get this, and also we get this, because exercise 13 in section 46 here, when m is not equal to n, the function the result of this is 0, and when m is equal to n, then the result of this is 1. So it is clear that summation m is equal to 0 to infinity am times integral g of g times g negative g naught to the m dg is an. Because when m is equal to n, because m moves to m changes from 0 to infinity, so sometimes m can be equal to n. In that case, just the terms arrive, which is exactly an. Okay, here n. So we have this result because of equation 5 and 7. Here is 7 and 5 here. From the equation 5 we get this for this and also from this is exactly integral along to control c g of g times f of g dg, which is another expression, but which is an here. And also for the same integral, we have this, the nth derivative of f at g naught divided by n factorial. So we get this. This proves that series 2, which means this, is in fact the Taylor series for f about the point g naught. Okay? We note that how it follows from theorem 1 that if series 1 converges to 0 throughout some neighborhood of g naught, then coefficient an must all be 0. Okay, next we are going to check second theorem, which concerns about the uniqueness of Noether series representations. Theorem 2 says if A series given by this, summation n is equal to n is negative infinity to infinity cn times g negative g naught to the n, which is equal to summation positive powers and plus negative powers converges to f of g at all points in some annular domain about g naught, then it is the Noether series expansion for the function f in powers of g negative g naught for that domain. We'll prove this theorem by using a similar way to the previous case, I mean theorem 1. The assumption of the theorem tells us that there is an annular domain about G0 such that this equality holds for each point G unit. Let G of G be as defined by equation 4. Oops. But now allow n be a negative integer too. Okay? N can be a negative. Also, let C be any circle around the annulus centered at G0 and taken in the positive sense. Then, using the index of summation m and adapting theorem 1 in section 71 to series involving both non-negative and negative powers of G negative G0, which is dealt in exercise 10, we can write here or there is 1 over 2 pi I times integral along to control C f of G dg divided by G negative G0 to the n plus 1 is equal to, okay, in this case, yeah, f of G is, yeah, Cm times integral the control C G of G times G negative G0 to the m dg. Since equation 6 are also valid when the integers m and n are allowed to be negative. Equation 9 reduced to this expression equality where n is 0 plus minus 1 plus minus 2, keep going this, which is expression 5 in section 66 for coefficients in the Laurent series for f for in the annulus. So we can prove the theorem using a similar approach as in the theorem 1. Okay, that's it.